So from mass percent, we can get to the empirical formula. Empirical formula is the lowest whole number ratio of the elements in a compound. It's not the formula that we generally use. The empirical formula is just a stepping stone to get to what we really want, which is the molecular formula. The molecular formula represents the compound as we find it in nature. So it gives the actual ratio of the atoms that we find in nature. The empirical formula gives us the lowest whole number ratio of atoms of each element in the compound. Empirical and molecular can be the same formula, but molecular will also always be a whole number multiplier of the empirical formula. And to get the molecular formula from the empirical formula, we can turn the mass percent composition into empirical formula. But to get from the empirical formula to the molecular formula, we need to know the molar mass of the compound, which is somewhat easy to measure with our instrumentation nowadays. We can measure mass of a compound quite readily. So in this problem here, we're going to derive the empirical formula of a tin oxide from the masses of the compounds present. So if we start off with 0.500 grams of tin, we react with nitric acid to give tin oxide. We end up with 0.635 grams of tin oxide. Well, we should still have all the 0.500 grams of tin, so the extra mass is going to be the mass of the oxygen. So we can get the mass of the oxygen by difference. So now we have the mass of tin, mass of the oxygen. So we need to turn this into moles now. So once we have our masses, we divide by the atomic mass to get the number of moles. And after we do that, we have some random value numbers. For tin we have 0.00421 moles. For oxygen we have 0.00844 moles. At this point, we divide all of our moles by the smallest value. That will give us the smallest value will become 1. All other values will be greater than 1. And in this case, it comes out to be essentially a whole number 2. So we just round it to the whole number 2, and we get our 2 subscripts: 1 for tin, 2 for oxygen, SnO2. They won't always come out to be a whole number, and hopefully have an example that will include the next step that we use. Here's the rule. Let's go through this. If we are starting from a percent composition, one of the simple ways to do is we just assume that we have 100 grams. This quickly turns our percent numbers into mass numbers. You can assume 1 gram, 10 grams, or whatever seems appropriate to you. But it's just simple to use 100 grams, and these percent numbers change into gram numbers. We divide our mass by the atomic mass, and we get moles of each element. We divide all of our mole values by the smallest mole value. And if we have a decimal portion, so if it doesn't round to a whole number at this point, we might have a decimal portion. So we look at the decimal, we identify what the decimal might be in terms of a fraction. So if we're close to a 0.5, that's 1/2. Close to a 0.3, 0.33, that's 1/3. Close to 0.67, 0.7, that's 2/3. So once we identify a fraction, we're going to multiply all the mole values now by the denominator of the fraction. At this point, we should have whole numbers for all our mole values, and this will give us our subscripts for all the elements. So if we have a percent composition, we want to get the empirical formula. So we have 69.9% iron, 30.1% oxygen. It was the empirical formula of our iron oxide. So we have We assume 100 grams, so we have 69.9 grams of iron, 30.1 grams of oxygen. Now we divide by our atomic masses to get the moles, so we have 1.25 moles of iron, 1.94 moles of oxygen. We divide by the smallest amount, so this will give us 1 mole for iron, but 1.55 for oxygen. So this is obviously not close to a whole number. We cannot round this to a whole number. So 0.55 is close to 1/2. So we multiply both of these numbers by the denominator, the 2. So the 1 for iron becomes 2. That 1.55 becomes 0.1. Now we can round this 3.1 to a 3. We have a 2 and a 3. That becomes our subscripts in the form of Fe2O3. So another example of this, so we have 59.1% manganese, 40.9% fluorine. We assume 100 grams, so we have 59.1 grams of manganese and 40.9 grams of fluorine. Divide by the atomic masses, we get 1.08 moles of fluorine, 2.15 moles of fluorine, 1.08 moles of manganese, 2.15 moles of fluorine. We divide by the smallest number, we get 1 and 1.99. That rounds to 2, so we have 1 and 2. So the formula becomes Mn1F2. Well, we don't have to write the 1, so MnF2.